Okay, hello, welcome to this chemistry video. Today we are going to be talking a little bit about chemical tests. So, what are chemical tests? Chemical tests are these analytical tests that allow us to identify unknown substances. So say we have a test tube that has this unidentified salt or gas and we want to know what's in it, like what it's made up of. We can use these tests to figure that out. So in this specific video, we're going to be covering the test that you have to know for the Pearson Edexcel International GCSE course for chemistry. So this includes some common gases, some anions. So if you've forgotten what anions are, they're negative ions. Cations, so these are obviously the positive ions, as well as we're going to be talking a little bit about water. So that includes testing for the presence as well as the purity of water. So let's start with gases. So hydrogen. What we're going to do is in this test tube, we've got our unknown gas. We don't know what it is. Could be hydrogen, could be oxygen, could be chlorine, who knows. So in there, we're going to take our lighted splint. So this is kind of like a little wooden stick and it's lighted, so it's got a flame on the end. We're going to take this, we're going to hold it over the mouth of the test tube, and what you're actually going to hear is what we refer to as a squeaky pop. So it's this little sound. You want to remember these words, squeaky pop. It's what the exam boards look for. And this is actually the hydrogen, so that's assuming that our mystery gas is hydrogen, reacts with the oxygen that's just found naturally in the air, and it combines explosively and water is formed, and then that's why we hear this little squeaky pop sound. So that's that. Now moving on to oxygen. So oxygen's similar but a little bit different. Again, we've got our splint, but this time it's not lit, it's just glowing. So this means that it was lit maybe a few seconds ago, but we just blew it out, and it's still kind of glowing on the end there. So what happens when we take our splint and hold it over the mouth of our test tube containing our mystery gas? Well, ta-da! It relights. So the flame will reignite. The stick will be on fire once again. So that's that test for oxygen. Now let's move on to chlorine. So chlorine gas, we're going to, again, it's our mystery gas is inside our test tube here. We can take litmus paper or even universal indicator paper, and we're going to hold it just over our test tube with our gas in it. And what's actually going to happen is, if it's red litmus paper or kind of universal indicator paper, it's going to get bleached, so it's going to turn white. And so that's that one. If it's blue litmus paper, it's a little bit different. It will, when we hold it over, it will first turn red and then it will turn white. But in the end, it will turn white. It will get bleached. We say it has been bleached by the chlorine. Now, ammonia, when we take our red litmus paper and hold it over, it will turn blue because ammonia is an alkali gas. So it will turn blue, the litmus paper. We know that litmus paper is an indicator for acids and alkalis. Okay, something important to note about this when we're using this litmus paper or universal indicator paper is that it must be damp. So that's to say slightly wet, and that's because it's going to dissolve some of the gas, and that's going to be what changes the litmus paper. So it needs to be important that you mention that it is damp litmus paper. Something else, I just included a little hazard symbol. Chlorine and ammonia gas can tend to be quite dangerous if you're inhaling, so you got to wear eye protection. You got to be careful, especially if you're asthmatic when you're doing these sorts of tests. Okay, moving on. We have carbon dioxide, so I'm sure a lot of you know what carbon dioxide is. This one is a little bit different. Instead of having our gas in here, this is actually lime water, or also known as calcium hydroxide. So that's what's in here. It's this solution, calcium hydroxide solution, also known more commonly as lime water. So what we're going to do is in through here, we're going to put our mystery gas or our CO2, but we're not sure if it's CO2 yet. So what's going to happen is this solution, in it, a white precipitate is going to form, and that's going to make the solution go, well, it can be described as cloudy or milky or chalky, but it's just not going to be clear anymore as a white precipitate is formed. And this white precipitate is calcium carbonate, or CaCO3, and this is a solid because, as I said, it's a precipitate, and what's also going to be formed is H2O, which is, the liquid that it's in. So that is that. That's all our gases, I believe. Let's move on to our anions. So, like I said, our negative ions. We're going to start with carbonates because it's pretty similar to what we just mentioned with carbon dioxide. What you're going to do is you're going to add a little bit of dilute hydrochloric acid to our salt sample, and then we're going to look for fizzing or bubbles of gas or any sort of indication that a gas is being given off. And then what we're going to do is capture that gas and test the gas in the same way that we would test for carbon dioxide, so by bubbling it through lime water. And obviously the same thing. If the solution turns cloudy and milky, chalky, that means that the salt had a carbonate in it. Okay, more anions. So we know our halide ions. So the first three ones are chloride, bromide, and iodide. For these, we are going to dissolve the salt in distilled water to form a solution, and then we're going to add enough dilute nitric acid to make it acidic. So the reason we're doing this, we're acidifying the solution, is to remove any impurities. And it's important to note that we want to use something like nitric acid rather than hydrochloric acid for acidifying it. Because if we were to use hydrochloric acid, for example, that would be introducing chloride ions. So it would show as positive for chloride ions because we just added them. So we want to use something like nitric acid. Then we're going to add silver nitrate solution. So this is where the test really starts. So if chloride is what was present in the salt, if that was the anion, what is going to form is silver chloride precipitate, and this is a white precipitate. If bromide is what's the anion that's present, silver bromide is going to form, and this is a kind of creamy sort of color. And then finally, for our iodide, silver iodide would form, which is yellow. So in all these three cases, a precipitate would form, but the color you can see slightly varies from white to cream to yellow. So these three equations, what we can see here, we actually call them ionic equations. They're not the full equations, but they are quite useful for illustrating what is happening, what precipitate is forming that causes this color change. A little note, you probably won't be asked about it, but occasionally these precipitates that form can slightly discolor over time, so they might turn a gray or a pale purple, but you really just need to remember chloride ions turn white, bromide ions turn it cream, and iodide ions turn it yellow. Okay, moving on to our final anion, we have the polyatomic anion sulfates. So this one, you're going to, again, dissolve the salt in distilled water to form a solution. Then you're going to add enough dilute hydrochloric acid. So this is for the same reason as the nitric acid. This is to acidify it, to remove impurities. Similarly, you don't want to use a sulfuric acid, because that contains sulfate ions. Again, the test would show up as positive for sulfates, even though that wasn't what was in the salt. It's just what you've added in the acid. So hydrochloric acid is a good option, nitric acid is a good option, that kind of thing. Then we're going to add barium chloride. So this is barium chloride if we're using hydrochloric acid. If we were to use nitric acid, we'd add barium nitrate. But anyways, adding barium chloride solution. Now, what's going to form is barium sulfate. So this is a white precipitate. So you're going to see the solution turns a little bit opaque, goes cloudy as a white precipitate is formed. That's what we're looking for. Okay, let's move on to the cations. These are my favorite, the flame tests. So flame tests they involve a Bunsen burner. You might have seen them before. So what we're going to do is we're going to take a wire, normally made out of nichrome or platinum, and that's because these wires are generally unreactive. so they're not going to kind of affect the results of your test. So nichrome platinum wire, you're going to dip it in some concentrated hydrochloric acid. Again, I've got my little hazard symbol, concentrated. It's a little bit dangerous. Don't get it in your eyes, don't get it on your skin. Be careful with that. And the reason we do this is to clean the wire, so remove any impurities that could affect the results, but it's also to allow some of the salts, the unknown salt that we're trying to test, to stick to the wire. So once we dip it in the HCl, we dip it to the salt, get a little bit of salt on that nichrome wire. Then we are going to hold the wire with the salt on top in a roaring Bunsen burner flame. And this, you'll see what will happen is that the flame will change color. And this, what color it changes, depends on the cation present. So if we have a lithium ion, the flame will be red. If we have a sodium cation, we're going to see a yellow flame. If it's a potassium ion, we're going to see a lilac flame. If we see a calcium cation, we're going to see this kind of red-orange flame. And then finally, last one we need to know is if it's a copper-2 cation, then we're going to see this kind of blue-green flame. And you want to remember, they're kind of particular about the names of the colors sometimes, so remember, copper is a blue-green, not just a green, and potassium is a lilac, you know? Just some little notes, you may be asked, you may not. Sodium is sometimes described as orange, but most of the time it's yellow. And also, some cations turn the same color. So strontium, for example, also turns red, but it's sort of a different shade of red. So often what people will do is they'll compare it to what they know is the exact sort of shade. So like they'll get a picture or whatever of what a lithium flame should look like and then compare that. Okay, sorry I got a little bit interrupted there, but I'm back. As I was saying, there is another way that we can test for the presence of some cations. So this is through using a sodium hydroxide solution. So what we're going to do, we're going to make a solution of the salt by dissolving it in distilled water. We're going to put about 1 centimeter cube in a test tube, going to add about the same volume of dilute sodium hydroxide solution. And what's going to happen is, in some cases, a precipitate will form. So I say in some cases because for cations like sodium and potassium, the hydroxides of those metals are soluble. So the test doesn't work for those. It just works for a few of the ones I'm going to mention here. So let's start with copper-2. So the copper-2 plus ion is going to react with 2 hydroxide ions. And what's going to be formed is copper hydroxide. So you'll see in a sec as I write the state symbol, this is a solid. So this is a precipitate. You're going to see a precipitate formed, and the color of the precipitate is what you're looking for, and that is blue. Similarly, kind of the iron 2 is going to follow a pretty similar pattern, except the precipitate of this one is going to be green. So that's what you'll see. And then finally, we've got iron 3. So because of its different oxidation state, the reaction is slightly different. The product formed will be slightly different. You can see a 3 instead of a 2 here, and that means that a brown precipitate is going to be formed. Something interesting to note, not that you'll really need to know this probably, but sometimes when you're testing and it's iron 2, a little bit of brown might actually show up near the top as some of the iron 2 gets oxidized to iron 3, but primarily it will be green. I don't think you need to know that. Now, ammonium is a little bit different. Ammonium will not form a insoluble hydroxide, What instead will happen is when heated, when warmed gently, don't allow it to spit, that can be dangerous, but when warmed gently, a gas will be given off, and this gas is, probably guessed it, ammonia gas. Now, previously on in the video, I told you how to test for ammonia gas. So what you're going to do is you're going to carry out that exact test. You can see here, water is also formed. But what we're really focused on is the ammonia gas, which we can test. And if you remember, it's the red litmus paper. If that red litmus paper turns blue, that means that it was an ammonium ion that was present in the salt. Now, finally, it's been a long video, sorry. We're we're going to talk about a little bit about water. So if we're testing, if we've got a salt or a liquid, and we just want to see if water's in it, even it could be the smallest bit, but if water's in it, we're going to drop a little bit into anhydrous copper sulfate. So this is a little copper salt, but the thing about it is it's anhydrous, so it lacks water of crystallization. And when it's in this form, it's a white powder. But when we add water to it, we're going to form some hydrated copper sulfate. And I'll just write out the formula for this. So it's very similar. It's just like this. So you can see this little dot represents water of crystallization. And what is so important about this is that this is actually blue. So the powder will turn blue, and if it does, that tells us that there was water in whatever we just added to the copper salts. So copper salts, a little note about safety, they can be quite dangerous, so avoid getting them on your skin and all that. But yeah, so what you need to know, the powder will turn from white to blue as water of crystallization is replaced. And then finally, if we've got a liquid, we know it's probably fully, or we know it has water in it, but we're not sure if it's totally water or if it has some other things in it, we can measure the boiling point or the freezing point. So as you probably know, boiling point is 100 degrees Celsius and freezing point is 0 degrees Celsius. And that's at 1 atmosphere pressure, at standard pressure. But if there's any sort of deviation in this, so if it's lower or higher than any of these temperatures, that means that it's likely not pure water and there are other things mixed in with it that will be affecting its boiling point or freezing point. And then that's everything. It can seem like a lot, so feel free to rewatch this video, make infographics. Like it can be a lot to remember, but you can definitely manage it, I'm sure, and see you for the next one.